To measure the strength of the current, we require an ammeter. Theory of moving coil galvanometer. If I want to measure voltage, output voltage, I will connect an voltmeter here. Capital B, uniform magnetic field. Because of that suspension, there will be that galvanometer measures the strength of current. No. Hello students. In my today's class on magnetism, I shall discuss a very important topic, something called as a moving coil galvanometer. We shall understand the construction of the MCG, the so-called moving coil galvanometer, the theory behind its working, and finally we define two important parameters, two important quantities. One is called current sensitivity and the other one is called voltage sensitivity of the galvanometer. Now, so without having time lag, we shall understand the concept of moving coil galvanometer. Hope all of you have used a pointer galvanometer in your laboratory. I repeat, we are familiar with the usage of a pointer galvanometer. My dear students, why did we use a galvanometer for? It is to check the presence of current in a circuit. There is a misconception about a galvanometer. It is said that galvanometer measures the strength of current. No. A galvanometer checks the presence of current or even gives the direction of current in a circuit. To measure the strength of the current, we require an ammeter. So galvanometer is basically used to check the presence of current, and this is a special type of galvanometer, what we call as moving coil galvanometer. Now, this is the diagram which represents a moving coil galvanometer. To begin with, let us understand the principle of working of MCG. MCG ಅಂದ್ರೆ ಮೆಲ್ಬರ್ನ್ ಕ್ರಿಕೆಟ್ ಗ್ರೌಂಡ್ ಅಂತಲ್ಲ, ಮ್ಯಾರ್ಲೆಬನ್ ಕ್ರಿಕೆಟ್ ಗ್ರೌಂಡ್ ಅಂತಲ್ಲ. My MCG here is a moving coil galvanometer. In short, what I call as MCG. A moving coil galvanometer works on the principle that current carrying conductor. Any current carrying conductor placed in a magnetic field should experience some torque. Fundamental ಏನು ಹೇಳಿದ್ವಿ? Any conductor placed in a magnetic field experiences some magnetic force. Elevating my thought, here I call the magnetic force as torque, and I say this is the working principle of MCG, moving coil galvanometer. So what was the principle, students? You place any current carrying conductor in a magnetic field, it has to experience a torque. Now, let us understand the construction of an MCG, how a moving coil galvanometer is built up or constructed. MCG consists of a rectangular coil. So this is the rectangular coil I am talking about. P, Q, R, S. So an MCG consists of a rectangular coil of several turns of insulated copper wire. We take a rectangular coil insulated with tightly wound copper turns. The insulation is done using copper wire placed on a non-magnetic frame. This coil is placed on a non-magnetic frame. What happens if it is placed on a magnetic frame? Earth's magnetic field may disturb the deflections of the coil. Therefore, it is placed on a non-magnetic frame. The coil is suspended using phosphor bronze wire. This coil is suspended using phosphor bronze wire. Why? Very specifically phosphor bronze. Later you see the couple per unit angle twist is minimum for this material. So I use phosphor bronze wire. Now I need magnetic field. So what should I do? I place the coil between the pole pieces of a magnet. I take a magnet, powerful magnet, and place the rectangular coil between the pole pieces of that magnet. A small mirror is attached to this coil, not to see our face, not to know how beautiful we are. Then what is the mirror doing? It is to measure and observe the deflections in the coil. It is suspended by a wire, no? So naturally it has to deflect. The deflection is measured and observed using a small mirror. T1 and T2 are the terminals for external connection. Andre, if I want to measure current due to the deflection here, I connect an ammeter between these terminals. If I want to measure voltage, output voltage, I will connect an voltmeter here. So T1 and T2 are the terminals for external connection. So this is how an MCG is constructed. Now going to the theory. This is principally asked in the exam. Theory of moving coil galvanometer. What do I actually study when I say theory of an MCG? Here I am deriving an expression for current which flows through the galvanometer. My dear students, when I say about theory of an MCG, I am simply deriving an expression for current which flows through a moving coil galvanometer. Now, this is the rectangular coil P, Q, R and S, as shown in my earlier diagram. P, Q, R and S is the rectangular coil which is placed in a uniform magnetic field, what I call as B. P, Q, R, S is the rectangular coil placed in the uniform magnetic field B. N number of turns in the coil. That small n is indicating number of turns in the coil. L represents the length of the coil. Small n, number of turns in the coil. L, the length of the coil. B, breadth of the coil. B, magnetic field, as I have already told. I is the current flowing through the coil. So descriptions of that coil. What is N? Number of turns in the coil of the galvanometer. What is L? Length of the coil. B, breadth of the coil. Capital B, uniform magnetic field in which the coil is placed. I, current flowing through the coil. Now, if you observe carefully, the horizontal sides PQ and SR do not experience any magnetic force. Quite astonishing. I had told the moment a current carrying conductor is placed in a magnetic field, it has to experience some force. But now I say the horizontal sides, this horizontal sides PQ and SR they do not experience any force because they are parallel to the direction of the magnetic field. See, we know the expression for force on a conductor is BIL sin theta. It's a conductor carrying current. So force equals BIL sin theta. If it was a charged particle, very easy, sir. QVB sin theta. Now, PQ and SR are parallel to the direction of the field. So, theta becomes equal to 0. Therefore, F becomes 0. That is why I say horizontal sides PQ and SR do not experience any force as they are parallel to the direction of the magnetic field. Now, the vertical sides PS and QR, PS and QR, these are the vertical sides. They should experience some force. Why? They are perpendicular to the magnetic field. Horizontal sides parallel to the magnetic field. Vertical sides perpendicular to the magnetic field. So they experience a force F equals BIL. How? From the previous expression. Here N is the number of turns. Now, if you observe here, the rectangular coil is suspended by a wire. What was the material of the wire? Phosphor bronze wire. Because of that suspension, there will be some deflections, and that deflection is due to the deflecting couple two equal and opposite forces. See, observe, there is a force acting on QR, force acting on PS. They have the same magnitude but act in opposite direction. Couple. And what is this couple doing? Deflecting this coil. Therefore, the moment of the deflecting couple, I call CD, is force into perpendicular distance between the forces. So how is that? We have defined moment of the deflecting couple. CD equals force into perpendicular distance between the two forces. Force, the magnitude is NBIL. Force, NBIL. Perpendicular distance B, length into breadth area. So the deflecting couple is given by NBIA. What is A? Length into breadth, which is the area of the coil. So I repeat, the moment of the deflecting couple which deflects the coil, CD is force into perpendicular distance between the forces. So force here, magnitude of force NBIL. Perpendicular distance is A. This length into breadth is area. So deflecting couple is NBA. Now, further, the coil is connected to TH, thorium allado, torsional head, small ball bearing, which will again deflect the coil. Torsional head ant karitivi. Therefore, the torsional couple, because of the torsional head, is given by CT equals C into theta, where theta is the deflection in the coil. So I have a deflecting couple, I have a torsional couple. Very clearly, at equilibrium, deflecting couple should be equal to torsional couple. The deflections caused due to the coil couple is equal to torsional couple, or NBIA is C theta. I am equating them. Very early itself I told, what is our aim here? To derive an expression for current flowing through the coil. So I becomes equal to C theta divided by NBA. This C into theta divided by NBA. This C divided by NBA is a constant. C, couple per unit twist, is a constant. Number of turns in the coil is a constant. Magnetic field is constant. Area is constant. And that constant is replaced by K, which is called reduction factor of the MCG. So the constant K, which is C divided by NBA, is called reduction factor of the MCG. Therefore, if you see, I is proportional to theta. If there is large current flowing through the coil, deflections in the coil is more. If the current in the coil is reduced, theta also reduces. And this is the practical purpose, practical principle of a galvanometer, i.e. proportional to theta. Now, MCG is a huge setup. I cannot carry it from one place to another. It is not portable like your pointer galvanometer. Therefore, it is not used very frequently. Coming to the next definition, something called current sensitivity. We had I equals C theta divided by NBA. From my previous expression, I equals C theta divided by NBA, or theta by I is NBA divided by C, and this factor theta by I is called current sensitivity of an MCG. How do I define current sensitivity now? Suppose this is the galvanometer whose pointer is showing 0. And you know, there are 0 to 30 divisions on each end of a galvanometer. On either ends of the galvanometer, there are 0 to 30 divisions. 1, 2, 3, 4, etc. Again 1, 2, 3, 4, etc. If the pointer of the galvanometer has to move by one division from 0 to 1 or 10 to 11 or 29 to 30, it has to move by one division. Some amount of current is required. That itself is called current sensitivity of the galvanometer. Current required for unit deflection. How much of current is required to move the pointer by one division is called current sensitivity. The next one is called voltage sensitivity. It is defined as the deflection produced in the galvanometer per unit voltage applied to it. When I apply 1 volt of potential to the galvanometer, how much of deflections is produced is what is called voltage sensitivity, given by this expression. So my dear students, today you have learnt about MCG and 2 important parameters linked with it: current sensitivity and voltage sensitivity. My last session on this chapter, in the next class, we will understand how to convert an ammeter into a galvanometer and a voltmeter into a galvanometer. Until then, go through the previous sessions. We will meet in the next session. Thank you.